Okay, so welcome to this lecture on the topic of sample size. Sample size is obviously super important because when you start any study, you have to determine beforehand at what point you're going to start recruiting participants. I do want to flag that in this lecture, I have deviated from the promise I've made in previous weeks to avoid statistics. The reason is twofold. Firstly, because statistics play a really important role in the decision process behind sample size. You can't really separate the two. Secondly, because I know a lot of students actually enjoy the statistical component of the course. Some students hate it. For those students, I have made sure that I've signposted the actionable points. So by that I mean, if you want to estimate a sample size, what is the bits of information you need, and where do you find them, and how do you use them? Okay, so you do not need to have a full working understanding of the statistics that I talk about today in order to be able to use the information to accurately estimate the sample size that you require. That said, I know lots of students enjoy the statistics, and even if you're not a big fan of statistics, I think the way that I teach, I should highlight to you that I was the bottom set maths at school, and I really struggled with statistics during undergraduate. What really helped me was when I learned to use R actually, was I learned to plot distributions. And by being able to see what's going on, that really helped me figure out what was going on and to get more comfortable. So that's what I do in my lecture. I've only got one formula, or I think two formulas that I present on one slide. And the rest of it is all I teach visually. Okay, so even if you don't like statistics, you might find that the way I teach might help. The key learning outcomes today, I will discuss the 4 components that you need to be comfortable with in order to estimate sample size. Start easy and get maybe a little bit harder in terms of power, depending on your familiarity. Then I will be briefly summarizing why sample size matters for credible science. And then in another video probably I'll be demonstrating how to use the calculator that I provided for you. That calculator I have already made available a file where I walk you through how to use that calculator, and many of you have already used it, so and tell me that you've done it fine. It's actually really simple. Two of the values you can just use default numbers, the power and the alpha. Even though I'm explaining what they are today, you can just use the defaults, so 0.05 for the alpha and 0.80 for the power. So that only leaves you to identify what the experimental design is and what the effect size is. Regardless though, you will need to know this. As future researchers, and more importantly as consumers of researchers, these issues that we talk about today are super important for understanding research. What's good research, what's bad research, how do you do both? If you look at the main journals in psychology at the moment, so these are 3 of the highest impact journals, Psych Science, Journal of Experimental Psychology General, or JAP General, and the Journal of Personality and Social Psychology. They all request, when you submit a paper, they all in the submission guidelines state that you have to justify how you arrived at your sample size. Okay, so it's something you will need to do for your research, even if your research is just a final year project. Alright, so starting with the 4 components required to estimate sample size. The first is very simple. It's the experiment design. You have to look at the study that's either been done or that you intend to do, and you have to ask, is it experimental or correlational? Now I understand that you haven't actually been taught what a correlation study is yet in 121, so maybe you don't actually know what an experiment study is because you don't know the contrast. So an experimental study is what we've been discussing so far. It's essentially when you have 2 conditions or more, and the experimenter manipulates a variable and then looks to see how it impacts on another variable. So let's say a Professor Starbucks example gave half the students or participants coffee, the other half didn't get anything, and then measured their rating on how alert they reported feeling in lessons on a scale of 0 to 6. So it was a 7-point Likert scale, starting from 0 and going to 6. 6 meaning super alert today, 0 meaning was completely tired, completely dead today. So that's an example of experiment, because you are the experimenter. Let me just turn the pointer on here. The experimenter has manipulated a variable and is looking at how that variable impacts upon a dependent variable. So that's what we've been discussing most of the weeks. A correlation is simply, does one score predict another score? In other words, if I score high in one measure, do I score high in another measure? A simple example would be, if I scored high on how much I like coffee, so I really like coffee, you would expect me to have high coffee frequency, okay, of consumption. So if I don't like coffee, I should have very low coffee consumption in terms of how much coffee I drink. Okay, so you should see like a relationship like this, where if I score high on how much I like coffee, I should score high on how much I drink coffee. Let me give you some examples, rather than using my hands, let me give you some examples uh, that I've got from the internet. So here we have, does intelligence predict income? So you might think that it does, and this upward slope here indicates that it does. To some extent, there's a positive relationship here, such that the more intelligent you get, the more higher income you tend to earn. However, the test that we do in psychology, it's a Pearson correlation test, is actually quite small. So the Pearson correlation can range from 0 to 1, and as you can see, it's 0.2. So 0.2 is small to medium, I guess. These results are based on this study here. And so you can see that there's actually quite a weak relationship between how intelligent someone is and the income that they earn. Okay, so what that means is that generally, if you have low intelligence, you generally score low income. But as you can see, the relationship's weak, because there's some people that have generally low intelligence that have quite a high income. Okay, so the relationship here is weak, as indicated by the coefficient of 0.2. This is what a coefficient of 0.46 looks like. So the relationship between life expectancy and healthcare spending. This is, as you would expect, the more that a country spends on their healthcare, generally speaking, the higher the life expectancy. Okay, and that's a kind of a medium to large effect. Okay, so those are the things that you need to know about the experiment design. Very straightforward and very simple. Things that you learnt about in the first 4 weeks of this module. Okay, the effect size. I'm sure you've heard something about effect sizes, but just for the purpose of this lecture, I'm going to review and explain in my own way. The effect size is essentially how big of a difference does your independent variable have on your dependent variable. Or if you're looking at relationships, it would be what's the strength of the relationship, the R coefficient. But for experiments, it's how big of a difference does it make? Now this is important. If you think of, and I'm going to explain why with this example. Imagine you were asked the question, is there an animal in this room? That's your research question, okay? So for the analogy, this is your research question. Is there an animal in the room? Your immediate answer to the question should be, well, it depends on the size of the animal, or in terms of science, it depends on the size of the effect. If you're talking about an animal / effect this big, then no, you don't have to look very hard in order to rule out the possibility that there's an animal this big in the room. If you're talking about an animal this big, then you have to look a little bit harder. And in terms of science, what the animals represent are your hypotheses. If you're predicting a big effect, if your hypothesis is that there's a big effect in the present, then you don't have to look very hard. You can run a few participants. If you're predicting a tiny effect or a small effect, then you will have to look a lot harder. In other words, you'd have to run a lot more participants. And hopefully what that shows you is that the level of how hard you have to look for an effect is influenced by how big of an effect you should expect there to be. So we can say there's good evidence that there is not a big elephant in this room, but we don't have very good evidence yet from looking this hard that there's not an animal this size in the room. Okay, and indeed, what we could do is recruit more participants, and what that essentially does is take away a lot of the noise. It zooms us in. Okay, so now we can see we have a better chance of finding our effect if we're looking for an animal about this big. And as you can see here, there is actually a cat hiding. Okay, so hopefully that's a helpful analogy as to why it matters how big of an effect you're looking for. Now, there are two types of effects that we can be interested in. There's the raw effect, the raw difference, and there's a standardized effect or a standardized difference. The raw effect is just whatever you're measuring. So if we're looking at, with our Starbucks example, if we're measuring alertness, then it's just a raw difference in the rating scale. So if we look at this graph here, on the x-axis you see we have our Likert rating, 0 to 6, and on this axis we have plausibility. Okay, I haven't put the label there, but there should be a label here saying plausibility. Now let's say that we plot our data from our study. Okay, so as you can see, we have the no coffee condition, who scored on average a value of 3, and we have our coffee condition, who have a mean of 3.7. Okay, so we can see here that we have what their raw score would be. The raw difference is just 3.7 minus 3. So they have our conditions had an alertness difference of 0.7. So that's a raw difference, and it's helpful to know, and usually it's what we tend to be interested in. We want to know how much will this weight loss program help us lose how much weight, and so on. You also should be familiar with the standard deviation. The standard deviation tells you how much participants in each condition differed from their means. So I've given them the same standard deviations in this example. So you can see on average people differed from the mean by 0.4. Just to give you an idea of the kind of information that helps us with, these two graphs were the same study, and they show the same raw difference. So both graphs show a difference. If you just calculated the means and took one away from the other, you'd have a difference of 0.7. And that's helpful. We know that drinking coffee increases alertness by about 0.7. But there's more information we can get from these graphs. If you were to take a person from the coffee condition and you were to ask the question, does this person score higher than the average of the other condition, you could be pretty certain the answer is yes. Okay, so random person, random student plucked out of the air, does that student have a higher score, that from a coffee condition I should say, plucked out from a coffee condition, does that student score have more alertness than the average no coffee student? The answer would be quite highly yes. There's some students down here, look, if you look at our distribution, some students down there that don't have such a high score as the average of a control, someone who hasn't drunk any coffee, but the majority of students on average would have drunk more, would have more alertness than someone in no coffee condition. That's still the case over here on this graph, but we have more variability, which means that more students that drank coffee still have a lower average score, or a lower alertness score, than the average of the no coffee condition. Okay, so we can be less certain, we still can be quite certain, because the effect size is still quite big, the standardized effect, which we'll get to in a sec. But we could be less certain. There's more participants that scored below the average of the control condition than when we have less variability. And that's what the standardized effect size does, is lets us incorporate that. Okay, so as you can see, I said there's same raw difference, but there's more overlap between the two groups. So the effect size, these are the only formulae I'm going to be presenting today. The effect size is, let me just start my timer, so make sure I don't run over today. The effect size is called Cohen's d, alright? And this is how you calculate it. It's just the effect size divided by the average standard deviation. Now in this example, the standard deviations in each condition are the same. So the average is going to be 0.4. Okay, but the reason why you don't just calculate the average is a little bit more of a fancy formula. It's because sometimes the standard deviations differ and are based on different numbers of people and so forth. So you don't just add them up and divide them by 2. You do this kind of fancy way of doing it. You don't need to worry about that. Essentially, it's the raw effect divided by the average standard deviation. In this case, we get a Cohen's d of 1.75. Now, anything more than 0.8 is considered really big. So, and the reason why this is so big is because, as we can see, there's not if you took somebody from the coffee condition, you can be pretty certain they score higher than half of the participants in the no coffee condition. Okay, so you get so that's the difference here. So there's a raw score of 0.7 and there's a standardized score of 1.75, and that 1.75 is much bigger than 0.8. So we consider that a really large effect. It's quite, you can think of it as reliable. Okay, here I show the same raw score. So the raw score is still 0.7, look, but you can see that we have there's more variability. So if you took someone from the coffee group, you could be less certain they scored higher than the average of the no coffee group. So, and that's reflected in the standard deviations. So now when we calculate the D-score, you see that it's come down to 0.8. Now this is still quite a big effect size. Yeah, you're still quite certain because so few participants in the coffee group score below the average of the no coffee group. But you can see that the standardized effect size reflects that there's more overlap, that you can be less certain about the effect that your coffee's had. Okay. And I just wanted to finish with a quick example of having the same variability but a smaller raw score. So now we have the means are only slightly different. So we can see there's a mean difference of 0.2, but which is the raw difference. So in terms of alertness, we only found the small effect size of 0.2, and the standardized effect size has come down a lot as well. Because again, if you now take a student that drank coffee, there's a lot of students, look, represented in this part of the dark blue graph, that demonstrate that scored less than the average no coffee drinker in terms of alertness. Okay, so you can be less certain that your coffee has had an impact if you were to select a coffee drinker. So that is why we used both measures, and both measures are super helpful. You shouldn't only report one or the other, and in fact, it's good practice to report both, which, as you will notice in your assignment papers, the original studies that you can choose which ones to replicate, you can see that both are reported. Now, we don't explicitly have to report the mean differences. So we report the means, and then people can calculate the mean differences if they want to calculate the raw score. And then you can also see that they've calculated Cohen's d and reported it for you. Likewise, in the Neckman's paper, you see the raw scores have been reported, and then they've also reported Cohen's d to give you an indication of how reliable of an effect this is, how much overlap there are between the two groups. So that's the effect sizes. Let's move on to the alpha threshold, and I'm not going to spend too long talking about the alpha threshold. For those of you that don't care about statistics, just want to know what you need to know, p equals 0.05. Okay, anything smaller than 0.05 is considered to be significant. And as you know, when you report your t-tests, you should report your p-values, and you can see here the p-values in Piazza et al. Are 0.004. That's smaller than 0.05. So we say that we reject the null hypothesis. We declare that there's an effect here. And likewise here, the p-value is smaller than 0.001. So we say that that's smaller than 0.05. Therefore, we reject the null hypothesis. So why do we calculate p-values? What is a p-value? A p-value is just the proportion. Well, let me explain it this way. Here we have a similar graph. So this represents our null hypothesis. So before I showed you a point null, which was just a straight line. Now this is how the statistical tests that you conduct, this is how they calculate p-values. They say that the null hypothesis is true. So all the tests you conduct are null hypothesis tests. So they say that the most likely outcome is 0. Values close to 0, look, so these values here are still quite likely. And values further away from 0, effect sizes really, and in this example I'm using Cohen's d, effect sizes far from 0 are increasingly less likely. So if there's nothing going on, the effect doesn't exist, right? You're wrong about your experimental hypothesis. There is no difference between these two conditions. You wouldn't be, the most likely outcome is 0. You wouldn't be very surprised to see a value of 0.5. You'd be a bit more surprised to see a value of 1. A bit more surprised, is a little bit less plausible in other words, to see a value of 1.5. And by the time you get to a value of 2, it's really unlikely to be the case that this was caused by the null hypothesis, because it's so implausible. And in psychology, we have the 5% rule, don't we? Where we put the area, so the area under the curve is, we say any value greater than the top 2.5% in either direction is so unlikely that we say it's unlikely to have been caused by the null hypothesis, and we reject the null. Okay, so these notes just explain that. Effects close to 0 most likely, effects far from 0 unlikely. When an outcome is sufficiently unlikely given the HO, we reject HO. HO, by the way, just means the null. Now, what you need to know about how we model the null hypothesis for these tests are that the more participants we have, the more certain our model of the null hypothesis is. Now, the model, by the way, just means it's a representation of our null hypothesis. It's basically how do we say values close to 0 are plausible and values far from 0 are implausible. Of course, if we have loads of participants, we can be more certain if the null is true that it's true. Okay, so here we have the first distribution I showed you had 5 participants. This is what the null hypothesis looks like with 5. Notice we can't really rule out very many answers. If we got an effect of 1, it's not that implausible given the null hypothesis of 5 with 5 participants. Therefore, we don't rule it out. We don't reject the null hypothesis. However, if we had recruited 50 participants, now look what happens. We're really certain about the about the effect size of 0. It's the most plausible outcome, and it's really plausible. And because we're more certain about this being the most likely outcome if the null hypothesis is true, values close to 0 are now quite uncertain. We haven't even got to d equals 1, and you can see now that even values smaller than d equals 1 are quite unlikely given the null hypothesis. The reason why is the area under the curve has to sum to 1. Now you can think of it as Play-Doh. Imagine you had some Play-Doh and you had n equals 5 here, but now you recruit more participants, so you want to say, well, if 0 is true, we can be quite more certain that it is true because we got more participants. So let's make that higher, but because you've only got one chunk of Play-Doh, as you make that higher, you get a thinner distribution. So that lets you rule out values closer to 0. So if we were to get a d of 1, if we had recruited 5 participants, we couldn't rule it out. We couldn't reject the null hypothesis. It's still somewhat likely given our model of the null. However, if we had recruited 50 participants, now it's really unlikely given our model of the null hypothesis with 50 participants. Okay, so that is the logic behind the p-value. Ultimately, as sample size increases, our hypotheses are represented with more accuracy, which means we can reject values closer to 0. So that's alpha. Now we get to power. Now this is the more in-depth topic, but if you understood, it doesn't take much more logic than what we've already covered. So power is the effect. If the effect exists, how reliably will you be able to detect it with your study? And it depends on 3 things: alpha, effect size, and the sample size. So as I just explained, this is the model of the null hypothesis. And it models plausibility, so values close to 0, most plausible, values further from 0, effect sizes further from 0 get increasingly less plausible, if the null's true, remember. Now, as you've seen, as we increase the number of participants, we get more certain about 0 being the most likely outcome if the null is true. It's more of a plausible outcome. And what that means is that we get thinner tails. Other values get less likely, assuming the null hypothesis is true. And when we get to 50 participants, this is what our model of the null hypothesis looks like. So let's compare 50 with 5. Okay, as you can see, 5 is much noisier. We really can't rule out values closer. With 5 participants, we can't rule out values close to 0, or even fairly far away. With 50 participants, we can rule out values quite close to 0. Okay, because we can be certain. And you can see that there's of course a difference then in our decision criteria, because if we were to get an effect size, say d equals 1, as I said earlier, if we had recruited 5 participants, we wouldn't have the statistical power to say, if this is true, if this is the actual effect size, we reject the null hypothesis, because it's not that unlikely given our model of the null hypothesis. However, with 50 participants, now we can say, look, given our model of the null hypothesis with 50 participants, because we're so certain, we can be so certain that 0 is the most plausible outcome, now we can reject an effect, the obtained effect of 1. Okay, so this is why it's important that when you plan your study, you think about what effect size you need, or what you might expect, and then that will influence if you want to recruit. If you're expecting your independent variable to have an effect size of about 1, you shouldn't be just recruiting 5 participants, because if you do so, even if the effect is true, let's say you obtain an effect of 1, you won't be able to reject the null hypothesis because it's not that implausible according to the null. However, if you recruited 50 participants and you obtained an effect size of 1, now it is implausible assuming the null hypothesis. So you have to make sure before you recruit participants that you think about what is the effect size I want to be able to rule out. Okay, now what I want to do is focus on just n equals 5 for now, because in the previous graph I showed you this is the expected effect size. But let's just pretend that we know. Okay, let's just pretend that we are God and we know that the real effect is 1. If this was the case, let's say we had this effect in the population. So this is everybody that lives in this circle here. And we take 100 participants out. Let's say you achieved an effect of, you found that the people that you recruited had an effect of 1.1. Would you be very surprised? Probably not. You probably wouldn't be too surprised. It's not that surprising because you're not going to have a perfect representation, a perfect sample that has the exact average of the whole population. So 1.1 might not be that surprising. 1.5 might be a bit more surprising. An effect size of 4 would be really surprising, especially if you knew that there's an only effect of 1. So rather than model our hypothesis with a straight line, we used distributions. So just like we model the null hypothesis with a distribution, we model the alternative hypothesis with a distribution. So this is just saying values close to 1 are the most likely given our experimental hypothesis. Values further away from 1 are less likely, but still plausible. And then values really far away from 1 are really unlikely. Okay, but still possible, but really unlikely. So it's the same logic, it's the same interpretation as understanding the null hypothesis. Notice though, if we were to obtain, say, a value of 1, that would fall outside of what we're able to reject. So let's say this is true. Let's say the true, as we know, in the world, in our little world we've created, there is an effect size of 1. Let's say we actually somehow recruited participants and found an effect size of 1. Okay, we recruited enough participants, we had a really accurate estimate, it was about 1.0001. We wouldn't be able to, our null hypothesis significance testing wouldn't be able to reject the null, because even though it's the most likely outcome of our experimental hypothesis, it's not that unlikely. It's not unlikely enough given the null. We won't be able to reject the null until we had a value of 1.46. Okay. In fact, in this example, we can calculate how much of our experimental hypotheses, or values that are probable under our experimental hypotheses, lies beyond what we would be able to reject according to our null hypothesis with an n equals 5. And only 30% of possible outcomes according to this experimental hypothesis fall beyond the p-value cutoff, the alpha threshold. So we would say this study has insufficient power. It's only got power of 30% or 0.3. So even if the effect exists, as we know it does in our little world, and it's a Cohen's d of 1, even if the effect exists, we wouldn't be able to detect it 70% of the time. Okay, so that's why we need to make sure we do high-powered studies. Now let's say we had an n of 50. Oh, and as I should say, by running small samples, what it means is, if the effect is true, you're going to even then create bias, because you're only going to publish, traditionally at least, before registered reports came along, you're only going to publish significant results, and to get significant results, you have to have large effects. So you're going to, because we don't know, we never have a world where we can just look into and create an effect size for. Because of that, we're going to overestimate our effect sizes, because all of the published research, the research that's significant, will have large effect sizes. Okay, let's see what happens when we recruit 50 participants. Now we have a much more narrow model of the null hypothesis. And of course, we also have a much pointier, narrow model of our alternate experimental hypothesis. Because we can be more, if it's true, we can be more certain that our predicted effect size is the most plausible outcome. Look what happens when so this, if you zoomed in now, you'll see that there's a little bit of purple in this space here. But now the vast majority of possible outcomes for, assuming that our model of our hypothesis is correct, that there's an effect size of 1 is correct, the vast majority of possible outcomes now lay beyond that alpha threshold of 0.05. It's now, most of the variables that are possible are so, if the experimental hypothesis is true, are so unlikely if the null hypothesis is true, that if we obtain them, we will correctly reject the null hypothesis. Okay, as you can see here, now we only need an effect size of 0.4. So if we obtain an effect size greater than 0.4, it means that we will correctly reject the null hypothesis, or hopefully correctly. Because remember, the reason why we have to play this make-believe game of pretending that the null is true, if the null is true, this is what the null looks like, and if the experimental hypothesis is true, this is what it looks like. The reason we have to do that is because we don't know which is true. Okay, so it's a constant battle between trying to make decisions between rejecting the null when it's false and not rejecting the null when it's true. Okay, so in this example, 99%, more than 99% of the possible outcomes, if our experimental hypothesis is true, lay beyond this threshold. Okay, so by running larger samples, it means you can find a significant result if the effect actually exists. But you should note that there is a trade-off, and that trade-off is that if the null is true, by recruiting more participants, you run the risk that maybe you just happen to get an effect size of 0.5, say. In this case, that means you would reject the null, even though it's true, just because you became so confident about your null hypothesis that the only plausible outcome really is 0, and all other values aren't. So there is a trade-off between type 1, incorrectly rejecting the null, and type 2, incorrectly rejecting the experimental hypothesis. Okay, I just wanted to quickly show, if you want to get a feel for this, how these components affect power and how you can influence it, there's a really good app that you can check out. Let me just get it up here. The app is, it was created by Daniel Lakens, who I've discussed previously in the past. And if I just show you here. Okay, so this is the app. You can go along, you can change the sample size. So here I've got the default is 50 participants with an effect size of 0.5 and a p-value of 0.05. And you can click, and no, you don't have to click anything, but let's just say, and you can see what happens to our distributions as you, so here I increase the effect size. So you can see if I go even bigger, now there's even less overlap. If we predict an effect size of 1.72, there's even less overlap. And you can see that our power has increased. We have basically 100% power. But if we had a really small effect size, now there's loads of overlap and we can't rule out, and most of our effect sizes, if the experimental hypothesis is correct, are ruled out. And we lose power, and we have a power of only 15% now. Okay, so I just wanted to include this, so just to let you play around with the distributions and look at what happens. I find this really helpful for figuring out myself how power, how it all works. Okay, so that is all of the components that you need to understand that go into estimating sample size. Okay, I've also touched on there a lot of research methods, but also a lot of statistics. All of your statistics that you're learning primarily use that kind of district modeling in order to make decisions, and that's really the process behind all the statistics that you'll encounter during your undergraduate. Okay then, so moving on to why sample size matters. I'm not going to go into too much detail because I think you've got a lot to work through, and I really recommend work through the first part of this lecture a couple of times if you need to. Okay, and do use that that Shiny app that I linked to in order to get a feel for how those components affect the power of your study. I should say that Shiny app has several graphs, but you really only need the top graph in order to get a feel for what the reasoning behind why we make decisions about the sample size required. So sample size matters because, as we've seen, you must recruit enough participants to find the effect, assuming the effect exists. So here, in this graph I showed you, very simple representation. Let's say we know for a fact that there's an effect size of 1. Knowing for a fact there's an effect size of 1, but only recruiting 5 participants would result in you not rejecting the null. You would run this study, feel really confident that there's an effect size of 1, but because you only recruited 5, and you can't rule out values less than 1 point, whatever it was, 1.4, 1.6 maybe, you would not reject the null hypothesis. You would have to conclude there's nothing going on here. If you had recruited 50 participants, now when you get an effect size of 1, you would be able to reject the null hypothesis. It's so unlikely, given the null hypothesis, that you would say it's implausible enough, we reject the null hypothesis, if the null hypothesis, okay? So, you have to recruit enough participants to make sure you can find the effect. As researchers, we need to make sure we don't waste resources. There's no point doing a study if the study it doesn't have enough participants to actually find the effect if it exists. It's also the case that the more participants you recruit, the more accurate your effect size estimate will be. So we also want to know, because we can never create a world and know that there's an effect size occurrence d of 1 in there. Okay, we have to sample from the real world little bits of the population and estimate what the effect size is there, and then we create an average of the effect size. And I know that this is, I know you've covered this. Tom Beasley was kind enough to share with me this script of his, and I know that you've already seen that so here, this is the IQ distribution. So this is a population scores, and if you were to recruit 2 people from this population, here we have those 2 scores, and here we have what the average those 2 average scores are. So if I were just to keep on recruiting 2 participants over and over, so here we have, look, that was bang on the average. That's quite lucky. Let's keep recruiting. Okay, so I do it again. This time you see we've recruited 2 participants. That's actually a little bit off from the center. So if we were to base our estimate of what the average IQ was based on these 2 people that we recruited, we would think that it's about 115, 120. But let's carry on recruiting. And eventually we'll find that we accidentally recruit participants that both just happen to be in the tail ends and would provide us with a really inaccurate average of scores. So here we have a score that we recruited 2 people at random from the population, and look how far from the mean that we actually have. And it's because it's 2 participants. Because we're only basing on 2, we just happen to take 2 participants that were really extreme examples, or fairly extreme examples, of the population. So if we were to base if this was our study, we recruited 2 participants and we estimated the effect size or the average IQ. Now we would assume that that the average IQ is much lower. What happens though if we increase this to say 50? Now we're going to sample 50 people from the population, and what you'll notice is in every case, we basically have a much more accurate effect size estimate. So our 50 participants are giving us a much more accurate effect size in terms of the average IQ score. So as you can see, every time the average is basically bang on the center. Okay, so that I know you're familiar with, this idea that the more participants you recruit, the more accurate your estimate is of the true population effect size. And if you recall, this is my slide on the reproducibility project from last week when we were talking about replication. And if you look at this graph here, the original studies estimated a much larger effect size than the replication studies. And indeed, in many cases, the replication studies found the opposite direction, which is what a negative score means here. But let's focus for now on why is it that the original studies may have reported larger effect sizes than the replication studies. The reason why is, if you ignore this for a second, I can demonstrate with an example that I found in a really nice blog post by a researcher called Jim Grange, and I highly recommend you read the blog post, but it nicely demonstrates just why recruiting small samples is a bad thing to do, and why it can lead to an overestimate of the average effect size. What he did was he created some data using R, so you can create data sets in R, simulate data sets, and he created from that and he basically created 2 variables, and these variables he correlated at 0.3. So he created a fairly small effect size. Yeah, it's not a strong relationship, but it's big enough that social psychology deal a lot with the kind of 0.3 strengths. Okay, and then what he did was he took 10 participants out of that data set 1,000 times. So he took 10 out, looked to see if it was significant, put them back in. Took 10 more out, looked to see if it was significant, put it back in. Okay, then what he did was he did it 1,000 times. And then he did the same for 20 participants, took them out, did a significance test, put it back in. Okay, and he did that with 20 participants, 30 participants, all the way up to 1,000. So at the end of his simulation, He was taking 1,000 participants out, doing a correlation test, seeing what the average correlation was for those participants between these two variables, putting them back in. Okay. And then what he wanted to know was if those 1,000 people found a significant effect, or if that sample, any sample, had a significant effect, he saved the effect size. Okay, so because remember, if you're a psychologist and you recruit 10 participants and you get a significant effect, you publish it. If you recruit 10 participants and you don't get a significant effect, you don't publish it. That's traditionally the way that it worked. Likewise, if you recruit 1,000 and you get a significant effect, you publish it. If you recruit 1,000 and you don't publish it. So remember, researchers traditionally have only had access to the significant effects, the ones that got published. So when they look at the literature and they say how big is this relationship between these two constructs, they're seeing these only the effect sizes that were significant. So what he then did was created a nice plot of the data. So here we have this plot. Now remember, we know, because he made up the data, we know that the effect size is 0.3. So that's what this red line means here. So with 10 participants, when you're looking at only the significant results, so remember, he's only looking at significant results, these are the ones that we have access to, look how much of an overestimate that is. The overestimate of the significant results for 10 participants, he found an effect size of about 0.75, I would put that at. Okay. Now notice this line here is the average effect size of studies that were significant for 10 participants. Now what we see is, as the sample size increases, the average effect size for those significant samples gets smaller. Okay, because as you remember, the model of the HO shrinks, so you can start to find some effect sizes that you previously couldn't rule out. You can start to rule out if you go back to the graphs I presented earlier. And what he found is, as he increased the sample size, the effect sizes became more accurate. Remember that we can't do this in real life because we can't really know what the average effect size is, but we have to use samples, and that's why we need it to be our samples to be as accurate as possible. And what he found is, as he continued to increase sample sizes, they kind of leveled out around 85 participants. So at 85, it was pretty much the correct number of participants needed to get an accurate estimate of the real effect size. And then after that, it just became slightly more accurate but more precise. So you can see that these error bars indicate significance. So for 1,000 participants, you're pretty much saying that values between just about 0.4 and 0.2 would have been significant. But notice how much more accurate that is compared to 0.6 to about 0.9. Okay, so this is a nice blog post that highlights why it's problematic to intentionally recruit small samples for the effect size that you're looking for, because it means that you can only large effect sizes will be significant, which then means when researchers look at the field, look at these papers that get published, and try to identify what the real effect size is, that people will think if the literature is made up of studies that only recruited 10 participants, you would think on average the effect size was about 0.7. In fact, the average we know, because we created it, or Jim Grange did, is 0.3. So this is a nice illustration of why it's harmful to intentionally recruit small samples. And it can lead to these outcomes, where if the real effect size is much smaller on average, but you're only publishing the studies that get large effect sizes, then you'll be misled about the true state of the world. Okay, that is why, because of these findings, that is why more and more in psychology you are being requested, and journals are now requiring you to justify your sample size based on the experimental design, based on the alpha and the power level that you want, and most journals require you have to have at least 0.8, and of course based on the effect size that you are anticipating. Usually, by the way, I should state that usually you rely on past research to justify, to kind of estimate the effect size you're expecting. But as you can see, because published research tends to have this bias, traditionally we've recruited samples that are too small. We say they're underpowered. Because of that, we now it's normal to kind of if you have a study that found an effect size of 0.4, one thing you can do is power for a smaller part of that. So one thing I recommend in my calculator is that you power for a third of the size of effect that's reported by original study. Okay, what that means is that if the original study that you're basing your the effect that you're expecting on is an overestimate, then you power for sufficiently below that to make sure that you can detect the true population effect size, which is what I tell you to do in my guide. Okay, so that is all of the statistical stuff. Hopefully you have a better idea now of how to of the reasoning behind the need to estimate the sample size ahead of time. And I'm now going to stop recording this and we'll jump over to the next video where I'll talk you through how to use the calculator.